Okay, and if you were here earlier, you heard that we've rejiggered the schedule, and I will be giving the last talk, which was earlier, supposed to be earlier, practical intensity-based meta-analysis. Thank you, Tom, for that introduction. Camille, well, it should be under me, but it might be under Malmet. It's under Nichols.
How many after one from earlier under Nichols?
Should have two.
Oh, I see it, sorry.
Yeah. So the purpose of this was to talk about practical methods for intensity-based meta-analysis. Now, the focuses of this session has been on coordinate-based meta-analysis simply because there is more of that kind of data around. But as evidenced by things like the Enigma project, which is pooling larger and larger numbers of original data together, and with the presence of things like Neurosynth, which is collecting, well, OpenFMRI, which is collecting the original data, and Neurosynth and Neurovault, that is collecting the Z-maps. I think the prevalence of the image-wise data is growing, and I think it's worth sort of considering what are the techniques that we'd put to use for that kind of data. I'm going to do the same if you don't mind. So next. Next. Okay. Actually, sorry. Next. That's a. Oh boy, there's going to be lots of these. Okay, so what happens in a typical fMRI analysis? We start with some preprocessed data, we fit a model to it, and we get a contrast estimate and a standard error. We usually do not look at those, but they are there. And the thing that we actually make inference on is the statistic map. And we make some decision about where is something there or not. That's the first level model. And of course, generally we work with second level models, so we need multiple subjects. And of course, you could look at the individual results for each subject, but generally we don't because we're interested in a group analysis. It's just that there's so many animations on this. And so we combine the optimal way to combine information across subjects is not just by using their contrast, but by using their contrast and their standard errors. This is what FEAT's flame analysis does, and also SPM does have a MFX option that's actually now available. It was always hidden there, but it's now usable. So this notion of combining information across subjects we're quite comfortable with and is routinely done, and the best way to do that is by combining both the estimates and their uncertainty together to get an inference. Now, and then of course we get an inference on that at the end. Now, what if we have multiple studies? So we have multiple groups of subjects. So normally we would be looking at this is study 1's result, this is study 2 result, and everything we've been hearing today has been based on picking out the peaks and then doing some analysis on that. And so you might think that this talk would focus on just, okay, how are we going to combine these maps? But of course, that's not the optimal way to combine them. The optimal way to combine different results from different studies is the exact same way that we combine results from different subjects. You need to combine the estimate maps with the standard error maps to get the optimal weighting between different studies. Like that. And so that's the crucial thing. So if we want the optimal combining of information across studies, we need to be combining both the estimates and their standard errors to get basically a meta-analysis estimate and a meta-analysis standard error. And then we can make inferences on that. Okay. And so this breaks down to subject level, and then and study level, and meta-analysis level. Maybe whenever I wave my hand. So this would be called a 3-level analysis in FSL for the subject study and meta-analysis level. Okay, next. So we're going to call this the gold standard approach to intensity-based meta-analysis. But it does require some things. Next. You need to have these contrast and standard error error maps available for each study. Next. And crucial to this is that they all must have the same units. Now, if you've used FSL all together in your own lab, that's not a big deal. But if you're going about trying to collect images from across different sites and different labs that maybe are using different methods, this can be an issue. Next. So, why are the units important? Well, if we're going to use the contrast estimates, next, there are 3 different locations where there are scaling that could come into the data analysis process, which may be different between different packages or different sites. So these are in the data scaling. So as you know, the data as it comes off the scanner has an arbitrary scaling. It has arbitrary units, and for example, FSL will scale the median brain intensity to be 10,000. FSBM does mean brain intensity to 100. So those are differences there that we would need to account for. Quite a profound difference, a 100-fold difference. Also, now when you do the model parameter estimation, next, there's lots of animation. So that's what I was just describing, okay. And then next, so this is how SPM finds the brain, and then next. As I mentioned at an educational talk a few years ago, also SPM does have has trouble finding the brain and produces a biased estimate, so it actually doesn't really give you a very good estimate of the mean brain intensity, but it's just another source of differences between packages. Next. Okay, next. Okay, the other source of differences is the model parameter estimation. Next. Next. Okay, so we have to build our design matrix whenever we fit fMRI data, and there are lots of different choices that you could make. Next. So in particular, some software scales the block design to be from 0 to 1, or it might do it differently. It might so for example, well, most of them, for long blocks, actually both FSL and SPM agree on how to scale block designs. They basically start at 0 and then eventually get up to 1. But for event-related designs, in fact, it's actually different and complex. I mean, you can decide to try to scale it to a unit height, but then if you have close events that are close in time, they might combine and then sort of make it difficult to see what is a unit height. And also, I think SPM scales it so that the sum of squares of the HRF are unity. So different ways to do it, and it's complicated. There might be differences between software. Next. And the last way that you can get differences is in the contrast. Next. So the contrasts, of course, are the thing that we use to summarize the parameter estimates and the regression and get the inferences that we care about. And one thing that's actually constructing contrasts is difficult enough as it is, and one thing that makes it easier is that they are invariant to the scale. So you might do a contrast of 1, 1, 1, 1, and I might do a contrast of a quarter, 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 and we will get the same T maps and the same P maps. However, if we then were to go and share our data into a common meta-analysis, our data would be off by a factor of 4 from each other. So this matters. Next. Next, please. So if you want, this just as an advertisement, I try to make a rule of whenever I do analyses to use a construction of the contrast that is guaranteed you to preserve the units. So if you've gotten the units just the way you want them here, and you've gotten your regressors to make sense here, if you use this rule so that the contrast, the positive elements sum to 1 and the negative elements sum to -1, that will give you a units preserving contrast. Next. Okay, so next. Next is just a summary. So it depends on the scaling of the data, the predictors, and the contrast. Next. And so if you want to do this sort of gold standard approach, you have to make sure that all those things line up across all the different sources of data. Next. Of course, all this is kind of irrelevant, right, if no one shares their original contrast data. And so the other form of data that can be shared or that is more easily to be shared are Z-maps. And that, of course, is what's available in NeuroVault. Next. So I just want to quickly review, if you are handed data that comes in the form of Z-maps, well, what are your options? Well, there are these different combining statistics. There are a bunch of, these are kind of the classic meta-analysis methods. I've mentioned them before. You can sum up the minus log p-values. You can take an average of the z-values. These will, again, these will give, this is nominally chi-squared. This is nominally normal, 0, 1. You can get p-values again. You can also, this is not really standard, but it can be done. You can actually do a random effects on the z's. It's kind of a non-standard thing, but it's allowing for the fact that we think different studies might have different there might be systematic variation between the studies that's best explained by allowing for some extra variance. So if you see, these things are kind of almost the same thing. It's just that we're allowing, instead of assuming that we've nailed this right at the exact, that under the null hypothesis, this averages are going to be exactly have a unit variance, we're actually saying, yeah, no, there's going to be more variability between studies. Next. The other thing you can do, which is pretty common, is to do another variant of this, the z averaging, which is a weighted z, which is to do a weight that reflects the square root of the number of subjects that went into the study, which hopefully makes sense. That a bigger study, that by putting all the results into z units, that means they have the same units across all studies. But if you have one study that had 10 subjects and another study that had 100 subjects, you want to give more weight to the study that had 100 subjects. And of course, all these things, the Stauffer's methods can be generalized into a type of meta-regression, even with these weights. Next. And then finally, you can do something that's actually kind of the easiest thing to do, and perhaps people have done if they've had a small number of studies around their lab. You can simply submit the contrast images from each study to a new analysis without knowing what the weights are. So this would be kind of an ordinary least squares approach, but it does account for random variation between the studies. Next. And if it were the case you actually had contrast estimates and standard errors, so this isn't implemented anywhere. Well, no, that's not true. The FSL does have a fixed effects option when you're combining different studies together. And this is basically saying that the variance is not actually estimated because it's just taken from the first level. And it's kind of equivalent to the Fisher's and Stauffer's methods that were on the top of the previous slide. But again, this is a fixed effects, not a random effects. It's not accounting for a between study variation. Next. Okay, so what are the options for these methods here? So the gold standard method is based on the contrast, the standard errors. It is available in these two packages. The other methods that are practical are the random effects GLM. That's where you just shove in the contrast from each study. Or the Stauffer's random effects, where you just study the z's of these, and you could do those methods. Presently, these methods are not implemented or available. Next. But for some shameless self-promotion, Camille Ahmed has been working on an SPM extension that will implement all of these different methods. It's definitely in beta software, but we're ready for other people to use it and welcome to have any feedback on that. Next. So when we applied that to a meta-analysis of 21 pain studies from Irene Tracy's group, what you see here are the mixed effects GLM, the random effects GLM. So these are kind of most closely hued to the standard, well, this is the gold standard, and then this is where we're not using the weights, we're just analyzing the contrast. This was using contrast and standard errors. These are pretty similar. There's not much difference between these. Now suddenly you're going to see a vast difference on these because these are the ones that are using the Z units. So this is a quite different beast. So we are losing some information here when we go from the contrast data to just working with the Z's. And certainly you notice back here, you notice how we're picking up some visual things here that we don't get with Stauffer's. And the difference between these methods, each side, these are all mixed effects or random effects methods, and these are all fixed effects methods. So this is saying that those effects there are probably attributable to just one or two of all the studies, and they don't generalize across all the studies, whereas these methods that are accounting for inter-study variation are saying, no, there's not consistent evidence there. But there's definitely sort of less rich information. I mean, basically, the reason why this looks so dramatically different is simply that the units of the information that went in were so different. And I don't mean the scaling units like I was talking before, but this was working on something that the mean of this model here has interpretation of percent bold change. What does the mean of the model that was fit here? Well, the mean meant average Z. So it just means something. This was an analysis of percent bold change. This was, in fact, all of these are an analysis of significance, the statistical significance of a result. Okay, next slide. Okay, so conclusions. Next. Of course, it's not often available, but when it is available, it is preferred to use the images and over the coordinate-based meta-analysis. Next. If you have all of the data from your lab and everyone has been using the same package, ideally FSL, it's not so hard to do the three-level analysis. As FSL is set up for that, and it's even in the support pages. But if you have data coming from heterogeneous sources, or if you're using SPM, it can be difficult to use the best practice mixed effects GLM. Next. And that's basically due to the units issues. It's very difficult to make sure that you got the same units between everything. Next. And so if you only have the contrast, the best thing is basically submitting those to a GLM as new. That works well. Next. And then for the tools based on the Z statistics, those are, there aren't so many tools, but we're trying to build those up. And we have a poster here talking more about the units problems and dealing with them in IBMA. So I'll stop there. Thanks for your attention. So any questions for me or any of the speakers that are left? I should say one example about units that reminds me how important it is when combining things. Once I had helping a colleague who was basically making SPM crash with a very normal analysis, like just generating NANs when the image data looked fine and fine. We eventually figured out they were trying to combine contrast from different studies, where in most of the studies the contrast was sort of active minus baseline or just average response, and the other one was a parametric modulation where the units were euros per bold percent per euro, because it was a reward task where they were doing a weight by how much more were you responding for every euro offered in response. And so there was a case where the units were such a problem that we're getting garbage, but even so much that the scales were so disparate that SPM couldn't deal. So it's very important to know that that's the extra challenge when working with the anything with the contrast, is that the units are equivalent and make sense to combine. Okay, so if there's no further questions, I'll close the session, and thanks everyone for coming. Let's thank all of our speakers.